Disruptions to global oil supply chains frequently expose a persistent vulnerability in how we move. Our mobility currently relies on the physical movement of fuel across vast distances. Internal combustion engines are tied to this mature but fragile refueling network. Without a constant flow from these global pipelines, the system stops. Viewed on the assembly line, the traditional engine is a marvel of self-contained mechanical engineering. It is designed to carry its own energy and convert it locally. This architecture means the vehicle's performance is largely insulated from external variability. Once the fuel is on board, the machine operates independently of the wider system. Electric vehicles represent the primary technical response to this fuel instability. But this transition is a complete redefinition of how energy is produced and consumed. It turns the vehicle from a self-contained machine into a node within a broader energy ecosystem. At the component level, electric motors are significantly simpler than combustion engines. They rely on basic internal copper windings rather than thousands of reciprocating parts. This mechanical simplicity provides immediate advantages: higher efficiency, instantaneous torque, and fewer points of physical failure within the motor itself. However, that simplicity is an illusion. The engineering complexity hasn't disappeared, it has moved. EVs invert the traditional paradigm. Their performance is now directly tied to grid capacity, charging infrastructure, and energy pricing. The engineering boundary of the vehicle now integrates directly into the energy system. While the motor is simple, the hardware required to manage the energy flow is not. Complexity now resides in the integration of high-voltage battery systems, power electronics, and thermal management architectures. Managing these systems requires sophisticated software control. Instead of mechanical linkages, we now rely on code to balance power draw and temperature in real time. This shift creates new requirements across the entire life cycle, from high-voltage isolation and thermal runaway mitigation to specialized recycling protocols for the battery cells. For automotive engineers, the primary internal challenge has moved from mechanical optimization toward complex system integration. The most significant system pressure occurs at the charging interface. This is where the vehicle's demand meets the physical limits of the electrical grid. To understand the scale of this load, consider that a single fast charger draws the equivalent load of dozens of residential homes. When many vehicles charge simultaneously, load coincidence occurs. Unmanaged, this concentrated demand can exceed the distribution system's capacity. This introduces immediate risks to physical infrastructure, including voltage instability and pushing local transformers to their thermal limits. These grid constraints are a core design consideration. Engineers must treat the stability of the grid as a primary design constraint for the vehicles themselves. Because the car, the charger, and the grid are often managed by different companies, diagnosing a failure becomes difficult. If a vehicle won't charge, it could be a software error in the car, a hardware fault in the station, or a load-shedding event from the grid. To bridge this gap, engineers rely on strict standards like those from the EM001 committee. These standards define the communication protocols and interoperability requirements that force these separate systems to talk to each other. Until this infrastructure and the grid can handle high-density loads, hybrid vehicles remain relevant. They function as transitional architectures that reduce the vehicle's total dependency on the system. Success in the EV transition depends as much on these communication standards and data protocols as it does on the chemistry of the batteries. The central challenge of this era is system ownership. Since the vehicle, the energy system, and the data platforms are controlled by different stakeholders, no single entity is responsible for the performance of the whole ecosystem. Engineers are now required to design beyond the edges of the vehicle, using risk-based frameworks that account for these interconnected, fragmented domains. The technical case for electric vehicles, higher efficiency and reduced oil dependency, is well supported by data. However, the future of mobility depends on how well engineers can integrate these fragmented systems to work together.